Bismillahirrahmanirrahim. Assalamu alaikum viewers and welcome to my channel. And in this video we are going to discuss here gamma integrals, because in the previous one in the last video we discussed integration by parts, all aspects of integration by parts, the terminating and the non-terminating integration by parts. Now after that, instead of moving ahead to the partial fractions, as I said in the last video, I think it's prudent to move ahead to the gamma integral, because in order to understand gamma integral and in order to understand its properties, we are going to use the integration by parts. Okay, so I think the next approach after integration by parts should be the gamma integral instead of partial fractions. So here we go. And the question might arise, what kind of integral this gamma function is. You see, gamma function is expressed by means of an improper integral. It is defined in terms of an improper integral, so that's why we call the corresponding integral as the gamma integral on the basis of the gamma function. Okay, as far as the improper integral is concerned, the integrand that we integrate in a semi-closed interval, they are called, such kind of integrals are called the improper integrals. You can see that we are having two types over here, this one. So you see, we are going to when we are integrating an integrand in a semi-closed interval, you can see that the lower limit is defined and the upper limit is not. So this is a semi-closed interval, closed at the lower side and open at the upper side. Okay, so that's how it looks like. So this you can see that both integrals, out of both integrals, one is not defined, so it is not a proper integral, it is improper integral. Same story is over here. You can see that the lower limit is undefined and the upper limit is well defined. It is a, it could be any real number. So the integration that we are performing over here is also in a semi-closed interval. It is open at the left side and closed at the right side. That's how it looks like. Okay, so you see, we define our gamma function in terms of our improper integral. So this integral in terms of a gamma function is called a gamma integral. All right, and it is represented by this notation. This notation represents gamma function. All right, you can notice here that the integrand is the product of two functions. One is of the polynomial nature, other one is the exponential involving Euler number. So the integrand is the product of two different functions, such that none of the function out of these two is expressed as the derivative of the other. So in order to evaluate in order to understand the properties of gamma integral, we are going to take the help of our integration by parts. So before moving ahead to the examples, it is very necessary, I must say it is highly mandatory, to understand the three major properties of this integral. And first of all, we are going to prove those properties in this video, and in the next part of this of gamma integral, I mean in the next video, we are going to have a look to couple of examples over there. Okay, so let's have a look to the three major properties of the gamma integral. So you see, these are the three major properties of this gamma integral. All right, so you can notice here in the first two properties there is a complete involvement of gamma function, but in the third property you can see that the gamma function is compared here, or it is equated to a factorial. So you see, this thing helps us to conclude that gamma function is falls in the category of a factorial function. But the major benefit and the superiority of the gamma function is that gamma function can help us to determine to help out the fractions as well as complex numbers, whereas factorial function only helps in determining the values of neutral and positive integers only. Okay, and on the other side, this gamma function also covers the fractions as well as complex numbers. But still, these two functions cannot be applied on the negative integers. So let's have a look to the proof of the first property here. So over here, I have to find out the gamma function of 1. I have to prove it that it is equals to 1. So just take the help of the general formula of your gamma integral. Substitute n equals to 1 everywhere. Wherever you find your n, you just put 1 over there, and then we are going to solve it out. So you see, it is going to be something like this. It is going to look like this. I just put 1 at this place. Okay. At the place of n, I'm going to put 1 once again. Alright, so you see you're having a 0 power on your x. So no matter what kind of base you're handling, if it carries 0 exponent or 0 power, it is going to convert it into 1. So at the place of x power 0, you just write 1, so no need to mention it. So simply now the integrand has been reduced to this form. Now you're going to apply the simple basic integration formula of the e of x. That's how it looks like. Okay, that's how it looks like. So just perform your apply this formula over here, and we are not going to put the constant because we are having limits here. Okay, so e power minus, sorry, I just repeated the step. It happens unintentionally. Okay, so we are just exponential integral is the exponential function itself, and then in the denominator we are going to take the derivative of the power. You can apply the substitution method as well, but it is further going to elongate. It's your choice, either you want to apply it or not. Okay, I didn't supposed to apply, I just did it directly. You can also take the substitution method. You just substitute your minus x to u, and then d of x will become minus du, and so on. So you can do like that as well. And direct work is also fine, just fine. Okay, so the derivative of minus x is minus 1. You are well aware with the derivatives, I hope. So now you are having something like this. Okay, how about if I just write my negative sign outside, and now I'm having this. And how about I write this e power negative x in the reciprocal form in order to convert my power into positive. So it is expressed like this. Alright, now we are going to apply the limit. Now we are applying the limit, so no need to write the mods. Open up with the square bracket. First apply the upper limit, then apply the lower limit, and you are taking the difference of these two values here, like that. You see you're having an indefinitely large value in the power, so the answer will be also indefinitely large. So it is going to be 1 upon infinity, and exponential having power 0 over here, it becomes 1. Alright, so you are having indefinitely large number in the denominator, so it means you are going to have the reciprocal is almost very close to 0, so you just approximate it to 0. Alright, so this thing is giving you minus 1, and gets multiplied with the minus sign outside, so you're having positive 1. So this thing tells that the gamma function of 1 is 1. That's how you do, and it is proved. Now let's move ahead to the next property. So here you go, the next property, and now we are going to integrate in order to prove this property. We are going to integrate our gamma integral by parts. Okay, by parts. So you can now if you have listened to my previous videos related to the by parts integration, I've mentioned over there that if you are having an integrand which is the product of the polynomial and the exponential, you always take the polynomial of the function to be integrated and the exponential as the function to be, I'm sorry, I just swapped. If you're having an integrand and the product of polynomial and your exponential, you always take the polynomial of the function to be derivated, okay, differentiated. And the exponential is going to be the function to be integrated while performing the by parts, okay? So this is something that I have briefly mentioned over there in the previous videos. Okay, so now we are going to handle these two functions separately because we have to apply here the by parts formula, which is this. I hope you're well aware with this. Okay, so we have to find the f dash and capital G of x one by one. So let us derivate this polynomial and integrate the exponential. Now let us differentiate both sides with respect to our x, the original variable. Okay, then we are going to get our f dash x, the derivative of our f of x. So okay, so it is going to be converted into f dash x. All right, and over here you're going to apply the traditional formula of your derivative of x of n, x power n. It is expressed as your n power x minus 1, like that. So over here your n is n minus 1, so the power minus 1. So this thing depicts that your f dash x is n minus 1 times x power n minus 2. All right, this is your f dash x. Okay, so this is it. Now over here you're going to integrate both sides with respect to your x, the original variable. My x looks like a horrible thing. Anyways, so okay, so the integral of your integration of this function will transform this small g of x into capital G of x, and now you're just applying plus some constant. So you are having this is going to convert it into minus 1. So this is your value. And while performing the by parts, you're not going to put down this constant c because still the process is going on. All right. So that's how we have obtained. Now we are going to insert these values f dash x, capital G, small g, f of x in this formula, which is representing the gamma function. Okay, so let's have a look over here. This is your f and g. Okay, now you're going to follow this right hand side of the formula, and it is your f and capital G. Your f is this, your capital G is this. Okay, so it is. And over here you're going to apply the limit minus integral with the limits f dash into g over here. Okay, so and you can see that this minus and this minus will be turned into positive. Okay, and this is a constant value, so it is going to be written outside this integral. So that's how it looks like. I have just placed this minus sign, this negative sign outside the mod like this, and then this negative and negative, I'm having a positive here. The constant value and minus 1 is written outside the integral. So this is the step that we have just obtained. Now you see I'm not performing any activity over here on this side. Now I'm focusing over here. All right, how about if I just write this e power minus x in the denominator, so it will be turned into e power x. Okay, so alright, so that's how this looks. It looks like. Alright, now we have to apply the limit here, the upper limit first, and I'm going to subtract it from the lower limit afterwards. So let me write down in a proper way. I'm applying the upper limit and x approaches to 0. Minus limit x is approaching to 0, like this, plus, now I have to write in a short fonts. Okay, that's how it looks like. Now you see, if I if I talk about this thing, once when I place 0 in the place of my x everywhere, then this thing will become 0, and this thing will become e power 0, which is 1. So overall I'm having a definite limit value, which is 0. But over here the case isn't that much easy. If you apply here infinity at the place of your x, you're having infinity upon infinity, which is an undefined condition. So over there, if you're having such kind of indefinite limit forms, then you just take the help of so introduced by a French mathematician, L'Hopital, that you just represent by this. And you apply the rule introduced by this person. Okay, so you see, let me just save this step and I just name it equation number 1 because I have to continue afterwards. Presently I'm just trying to explain how to handle this part. All right, so you see, if I just in L'Hopital rules, what you do when you just apply limit directly on this function, you are having infinity n power minus 1 upon e power infinity, which is in fact infinity upon infinity. So this is an undefined form. I'm very scared now what to do. So now what you do, you are going to derivate the numerator and your denominator, whatever you're going to get, then again you have to apply the limit, and you keep on doing this process again and again till you get a definite limit value in your hands. Okay, so you see, if I just first of all, once when I derivate this numerator, I'm having, you just apply the formula of this now, right? You are applying the formula, this thing, which is n power x minus 1, this thing. So I'm just applying this formula over here. I'm taking the derivative of your numerator, and is n minus 1 minus 1 gives you n minus 2 upon, and the derivative of your e of x is e of x itself. Then you apply the limit. Okay, once you apply the limit, still when you just replace x by infinity, you're once again you're having infinity. Still it is undefined. Now you keep on going, taking the derivative again and again. You see, this was the first derivative. All right, you take the second derivative again, then still it is going to be infinity upon infinity, because you can do it in your rough page to have an experience. So once when I take the second derivative over here, it's going to be n minus 2 x power n minus 2 minus 1 give you n minus 3 upon derivative of your exponential is itself. Then you again apply the limit. Okay, you apply the limit. Now once you apply the limit, still it is infinity upon infinity. So you keep on taking the derivatives n minus 1 time. The n minus 1th derivative is going to help you out here. So you see, once when you just keep on going and taking the derivatives, you keep on going and going. So you see 2.1, and then this was the stage, and then you're having minus 1. It is minus 1. I'm sorry for the lack of the space. So, and the derivative of the exponential is e of x itself. So let's sort it out. So you see, this is the, up till here, this is the factorial of your n minus 1. All right, and over here, once when you sort out this thing, it becomes, you open up the bracket here, it becomes minus 1 minus n plus 1, and this is the minus 1 over here. So you see, now this and this gets cancelled. You're now having x power 0, which is your 1. So the final form that you are having is this. Now you apply the limit. Now once you apply the limit, you are now having n minus 1 factorial, a number form in the numerator, and over here you're having this. So you are having infinity in the denominator, which will turn this thing into 0. Okay, now let me take the next page now. So this thing reveals that after taking n minus 1 derivatives on this function, having this limit, we are going to have a definite limit value. Okay, so once when we take n minus 1 derivative in the numerator and the denominator respectively, we are having this form. Then we applied the limit, then we are having infinity in the denominator, which reduces to the answer 0. Okay, so now we have just obtained a definite answer of the limit on this part, which is my 0. So, and this thing was already 0, so this thing will completely turn into 0. Okay, so this thing reveals this is your equation number 1. So now let me copy this equation in the next step to make a flow of work. So hang on, let me write it down. So this thing shows that the gamma integral of your n is, this is 0 minus 0, okay, plus n minus 1 infinity. And let me reduce it into a form n minus 2. Instead of writing n minus 2 over here, let me write it in a way like this. Okay, okay, so this thing now completely 0, so this is now 0 plus n minus 1. And now you can notice here that whatever the value you have over here in this integral, you just express it inside a gamma function. So if you can see the formula, whatever the value you have here, you just express it inside a gamma function. So this is something that I'm going to do over here. Whatever I'm having here is expressed inside a gamma function. That's it. Okay, so your n gamma function is expressed as n minus 1 times gamma function of n minus 1. So now let me replace n with n plus 1. Okay, so now in the place of n, if I write n plus 1, it is going to be like this. So 1 n minus 1 will get cancelled, and you are having n, and over here the same thing, you are having n inside the gamma notation. So this thing shows that the gamma function of n plus 1 is equal to n times gamma function of n. That's what your next property was saying. So it is proved and it's done. I hope you are a bit cleared how to resolve these properties. Now let's move ahead to the last property. Okay, so this is the third property that we have to prove. So this is our proof. Okay, now you have studied in the second property that your gamma function of n is expressed with this. If you replace your n by n minus 1, if you replace your n by n minus 1, all right, it looks like this equation is going to looks like, it looks like this. Okay, at the place of your n, you're writing n minus 1 minus 1 integral n minus 1 minus 1. So it is now n minus 2 into gamma function of n minus 2. All right, so you see the gamma function of your n minus 1 is equal to this. Is equal to this. Now you see at the place of your gamma function n minus 1, you can write this answer. Okay, so n is n minus 1 into gamma function of n minus 1, which is equals to this. Okay, now once again, when you replace your n by your n minus 1, you're now going to have n minus 2, and this thing is going to give you n minus 3. So once again, replace n by n minus 1. So now I'm sorry, it by n minus 2. It's going to be n minus 2. Okay, so I'm sorry, I messed up a little bit. You see, you have to replace your n by n minus 1 in equation number 2, okay, in order to get the gamma function of your n minus 2, okay. So you see I have replaced my n by n minus 1 in my equation number 2, and that's how I'm going to get the gamma function of n minus 2. So let me write over here n minus 1 minus 1, okay. I'm just working on this equation. So this thing gives me n minus 2, and it is equals to your n minus 3 into gamma function. That's it. So now you're going to substitute this value of this gamma function over here. Alright, so it looks like this: n minus 1, n minus 2, and in the place of your n minus 2 gamma function, you just write down this. Okay, so you see, you just keep on performing this process again and again till you reach to this form. We just keep on doing this. Till you reach to this form, and you can see that this is the factorial of your n minus 1 value. Okay, so the gamma function n is equals to n minus 1 factorial. Now how about if I replace my n with my n plus 1. Okay, so once when I replace my n with my n plus 1, it gives me n factorial. Okay, it is also expressed like this. This is the factorial, another notation of your factorial. So that's how it is proved, the third property of yours. The reason of proving all these three properties is because all these properties are very abundantly, it is getting applied in our exercise, in our questions related to the gamma integral. So once, if you are not aware, then you have no acquaintance with these properties, how they have arrived, how they have been derived, why they are here, what for they are here, there's no use of studying the gamma integrals. So whatever you study, you study deeply. Alright, so in the next video, inshallah, which is the part 2 of the gamma integral, we are going to discuss a couple of examples and how to solve the gamma integrals. Okay, take good care of yourself, and if you feel that this video has helped you in understanding the basic concept of your gamma integrals and the properties related to it, please subscribe my channel and hit on the like and share it with your friends and other learners. Take good care of yourself. I'll see you in the next video, inshallah, soon. Allah Hafiz.